Good day and welcome to theme 3.9, where we will be discussing the divergence theorem of Gauss, and this is also the last theme for theme 3. So previously we've done connotations of line integrals to flux integrals and to surface integrals, but now we are going to do the following. So basically what the divergence theorem of Gauss says is that if you have a flux integral, it can be equal to the volumetric integral of the divergence of your flux if the solid region that is bounded by your surface is in a positive orientation. So if you have a solid region, you have either outward or inward orientation. So in this case, you will have to have an outward orientation for a solid region to be able to use divergence theorem. So that is the only thing that you need. It needs to be a whole solid region, so it needs to be an enclosed region, and it needs to have a positive orientation. And then you can use divergence theorem, which can make your life a lot easier. So I'll explain it with the following. So usually if we saw this and we needed to get the flux integral for this type of surface, he would have had to break it up into two surfaces, surface 1 and surface 2, and get their parameterizations and have separate integrals for it. And then you would have the following. So then your flux integral would have been the sum of two flux integral. And we know, because we've practiced quite a lot, that doing this is quite a hassle. So basically, now all we need to do is get the volumetric integral for the surface, and then that will just give us our flux integral. So let's do an example of this. So they give us our flux equation, and they say S is the boundaries of Z is equal to x squared plus y squared, and x squared plus y squared plus z squared is equal to 2, around the region where they intersect. Determine the flux integral. Okay, so let's draw something for ourselves. So if you look here, this is basically what it looks like. So you have your sphere here, and you have your paraboloid, and inside here, this is basically where we want our flux integral for. So normally, if you didn't know about divergence theorem, you would have to break it up into surface 1 and surface 2, which is like the top part of the sphere and the bottom part of the paraboloid. So let's do that and see where we get that. So first thing you can do is surface 1 is the top part of the sphere. So then you can parameterize the sphere. Let's say you use cylindrical coordinates. And then you have r cos theta, r sin theta, r squared. And then you get the partial derivative of that towards r, which is cos theta, sin theta, and 2r. And then you get it towards theta, which is just negative r sin theta, r cos theta, and 0. And then you cross product that as follows, which will give you this. So now you have your cross product, and then you would have the following. So then you just turn your flux equation in terms of the cylindrical coordinates that you have determined. And don't forget the integrating factor that you have to add. And then you have your boundaries that go from 0 to 1. So basically you would have to see where they intersect to get the 1, and then your 5 that goes from 0 to 2 pi. And then you have to do this all over again for your second surface. So on second thought, let's get and try to see what this would look like. So if you take the divergence of f, so to get the divergence of f, you just take this derived towards x, this derived towards y, and this derived towards z. and then you add them together. So that would just give you 1, because derived towards z would just be 1, but the rest would be 0. So the divergence of f is 1. So let's say for this specific surface, you decide to do spherical coordinates. Obviously, remembering that you can do cylindrical coordinates as well, but spherical is nice for ball-shaped spheres. So we know that our theta goes from 0 to 2 pi because it's completely around. And then we know that they intersect where x is equal to 1, z is equal to 1, and y is equal to 1. You can go prove that to yourself. And then you can get your phi from that information, because we're looking at the phi here. So it goes from 0 to here. So our phi goes to pi over 4. So phi is in between 0 and pi over 4. So now we have theta and we have phi. But we only need rho. So how we got rho is we know that it goes from here to the outside. So basically, you take the equation for the sphere. We know that this part is equal to rho squared, and then you'll find that rho is equal to square root of 2. So then you have rho in between 0 and square root of 2. Now, since you have your boundaries, you add in this integrating factor that you get. And since the divergence of f is 1, you just add that in, d rho, d phi, and d theta. So it's a bit easier than actually going into the flux integral for both the surfaces. So that's just basically how theme 3.9 will be done. And this is equal to your flux integral.